Assalamualaikum warahmatullahi wabarakatuh, and hi there. In this video, we will explore on a new chapter on one-way analysis of variance, or simply a one-way ANOVA. What is it? This is what we are going to explore in this part 1 of the video. What about learning objectives that you should be able to achieve after learning this chapter? Let's find out the answers in the next slide. Let's look first at the learning objectives you should aim to achieve for this chapter. At the end of learning this chapter on a one-way ANOVA, you should be able to write down the statistical or probabilistic model or equation, the model assumptions, and a constraint underlying a one-way ANOVA. Next, you should be able to estimate the underlying model parameters. You should also be able to construct a one-way ANOVA table that consists of all elements that you must know how to calculate manually, which ultimately leads you to obtaining the test statistic suitable for a one-way ANOVA. You should also be able to perform the one-way ANOVA using the standard statistical testing procedure, which includes the statements of H0 and H1, the statement of the decision rule, calculation of test statistic value, identification of correct critical value, decision statement, and finally the sound conclusion. Next, you should also be able to use the simplest technology, which is using Microsoft Excel to perform a one-way ANOVA. Finally, you should be able to make the correct decision and conclusion either based on the manual calculation or based on the Excel output. Recall from Chapter 4 when you test a difference between two population means where the population variances are unknown and assumed to be equal, whereas the sample sizes are small. The case was classified as Case 3A, where you should use a t-test statistic as the correct choice of test statistic. The unknown and yet equal population variances are estimated by using the pool variance denoted by SP squared. So testing a difference between two population means, I repeat, between only two population means under those conditions or assumptions of equality of unknown population variances and small sample sizes, you will use a t-test statistic in Chapter 4. What if you want to test a difference between more than two population means under the same assumptions of unknown and equal population variances and small sample sizes? This is what we are going to learn and explore in this Chapter 5 on a one-way analysis of variance, or simply a one-way ANOVA. There is more than one method of analysis of variance which can be found in an extensive number of literatures. The methods include one-way, two-way, or k-way ANOVA with replications or without replications. However, in this course, we only focus on a one-way ANOVA, which is available in the Statistics for Engineers textbook, pages 127 until 139. You can also refer to many other references for clearer picture on this chapter. Why do we use a one-way ANOVA approach when we want to test if there is any difference between more than two population means? Here, one-way means one factor. The notation K refers to K factor levels or treatments or groups. For example, if we want to test if there is any difference between four population means, then K is 4. We assume that the groups are independent but share the common variances. For this chapter, the value of K should always be at least 3. If K is 2, then a t-test approach in Case 3A from Chapter 4 should be used. Back to the question again, why do we analyze the variance? when we are testing the means. Let's proceed to the next slide for more explanation. Before answering the question on why ANOVA, please look at this example 6.1 from the textbook to know better what a factor is and how we can identify the value of k. The question is as follows and the data given are tabulated as in the following table. Here, the one single factor is the alcohol, and the levels or treatments refer to the different types of alcohol. Since we have 3 different types of alcohol in this example, then K is equal to 3. Furthermore, the sample data at each level have the same or equal sample sizes. We assume that this sample data come from groups or populations which are identically and independently normally distributed with equal or common variances. We will further discuss on the assumptions when we learn about the statistical model underlying the one-way ANOVA. Back to the question again, why analysis of variance or simply ANOVA when we want to test if there is any difference between the population means? In this chapter, to learn about whether different groups have equal or different means, we consider the whole dataset as one set of data where the observations or data points may vary regardless of levels or groups. The one-way ANOVA approach then begins first with partitioning or decomposing the total variability of the whole data into 2 components. The first component is the between group variability. In alcohol example, the between group variability refers to the variations between types 1, 2, and 3. The second component of total variability is the within group variability. In alcohol example, the within group variability refers to the variations between the observations within the individual types or samples, either within type 1 alone or within type 2 alone, and so on. The second step in the ANOVA approach is to examine the ratio of the 2 measures of variabilities, that is, the ratio between group variability and the within group variability. Since we have a ratio of 2 measures of variability, then this can be done through an F ratio, indicating that an F-test statistic will be used and will be the right choice in this chapter. And hence, we have analysis of variance or simply ANOVA in testing a difference between more than 2 population means. Generally, the data for a one-way ANOVA can be in the following form with ith level or group from 1, 2 until k, where k is the number of levels, treatments, or groups considered in a particular study. The observations or observed values from the experiments or samples are denoted by Yij, where I, as you know, goes from 1 to k and j goes from 1 to ni, where ni is the ith level or ith group sample size. The sample sizes can be equal for all samples or can also be unequal. The sum of observations within each level is the ith level total denoted by yi dot for all I from 1 to k, whereas the sum of all observations or simply the sum of all level totals denoted by y double dot is what we call the grand total. This slide provides a statistical model which can be constructed under a one-way ANOVA and the underlying assumptions required when using a particular approach in estimating the unknown model parameters. The observed values denoted by Yij can be modeled or represented by this equation where Yij is equal to mu I plus epsilon ij, where, as you know from the previous slide, Yij is the jth observation from the ith factor level, or treatment, or simply from the ith group, where I goes from 1 to k and j goes from 1 to the ith sample size and I. The notation mu I is the ith level or group mean, whereas the epsilon ij is the jth random error from the ith factor level. The underlying assumptions include: first, the random errors are assumed to follow a normal distribution with mean 0 and variance sigma squared. Second, the random errors are assumed to be independent. And third, the value of error variance denoted by sigma squared is constant and does not vary. At this stage, the model parameters that need to be estimated are the k level means mu I for all I from 1 to k. If you have 3 levels or 3 groups, like in the alcohol example, then 3 level means mu1, mu2, and mu3 need to be estimated. Another unknown model parameter to be estimated is the unknown error variance sigma squared. How to estimate these parameters? This question will be answered in a later slide. But first, let's look at how to formulate the hypothesis statements for one-way ANOVA. For the statistical model we had earlier, each observation Yij can be a function of the ith group mean and the related errors epsilon ij. Therefore, we can test if all group means mu1, mu2, and so on until mu k are the same or not. Therefore, the hypothesis statements are written as follows: under H0, mu1, mu2 until mu k are all equal, whereas under H1, mu I is different from mu j for at least one ij, which means at least one level mean is different from the rest. One point to note: using a one-way ANOVA approach, if we reject H0, it means at least one of the group means is different from the others. But which one is actually different is not revealed by a one-way ANOVA technique. To check which one is actually different from the rest can be done through a pairwise post hoc test, which is not covered in this course syllabus. You may refer to other literatures for further reference. From the statistical model that we had earlier, the level of group mean denoted by mu I can be rephrased as mu plus alpha I, where mu is the grand mean or the overall mean, whereas alpha I is the ith level effect. Therefore, from the previous model of Yij equal to mu I plus epsilon ij, by substituting the level mean mu I by mu plus alpha I, we then get an alternative model or equation underlying a one-way ANOVA, which is given by Yij, which is the observed value, or in general the response variable value, equal to the grand mean mu plus the ith level effect alpha I plus the errors denoted by the epsilon ij, for I equal to 1 to k and j from 1 to ni. From the equation of mu I, the ith level effect denoted by alpha I is simply the difference between the ith level mean and the grand mean. In such a way, the ith level effect value can either be positive or negative, which means the treatments or factor levels can have different effect, either a positive effect or a negative effect on the observed values Yij. With the alternative model, we have additional unknown parameters that should be estimated, which include the grand mean mu and the ith level effect for all I from 1 to k. For example, in the alcohol example where we have 3 levels, then additional parameters to be estimated are the grand mean mu and the 3 level effects alpha 1, alpha 2 and alpha 3. The estimation procedure can be through a least square method, which is not covered in detail in this course. But using the method of least square, we shall have a constraint that the sum of all level effects must be equal to 0. Using the alternative model given by Yij equal to the grand mean mu plus the level effect alpha I plus the errors, we can have another set of hypothesis statements. Under the null hypothesis, when we assume all level means mu1, mu2 until mu k are equal, it actually implies that the factor levels or the treatments do not have any effect on the observed values or on the response variable Yij. Therefore, under the null hypothesis H0, we can alternatively write all level effects alpha 1, alpha 2 up to alpha k are equal to 0, which means under H0, no level effect or treatment effect exists. Whereas under the alternative hypothesis H1, a level or treatment effect can exist where its value is not 0 for at least one I for I equal to 1 up to k. A question you might want to ask: which of the hypothesis statements should you use then? The answer simply depends on the question or problem that you have. If you aim to investigate if there is any difference between more than 2 population means, then use the first choice where under H0 all mu1, mu2 up to mu k are equal. But if you are to investigate if a treatment or factor level has any effect on the observed values or not, then use the second choice of hypothesis statements that we have in this slide, where under the null hypothesis, no level effects exist against the alternative hypothesis where at least one level effect is not 0. What are the estimated model parameters? Let's recall the two models underlying a one-way ANOVA. The first model is this model, which contains the level mean μi in the equation, and the second model is this model, which contains the expression for the grand mean and the level effect alpha I. The errors epsilon ij are assumed to be identically and independently distributed with mean 0 and a constant variance sigma squared. So the model parameters in one-way ANOVA include the level means μi, the grand mean mu, the level effect alpha I, and also the error variance sigma squared for I equal to 1 up to k. Using the least squares method of estimation, which is not covered in this course syllabus, the corresponding estimates of these model parameters are given as follows. The estimated level mean, denoted by mu cap I, is the sample mean from ith group or ith level, which can be calculated by summing up all observed values within level I, which is simply the level total divided by the corresponding ith level sample size and I. The estimated grand mean, denoted by mu cap, is simply the overall or grand sample mean y double dot bar, calculated as the sum of all observed values, denoted by y double dot, divided by the total number of observations, denoted by capital N, where capital N is the sum of all level sample sizes. By taking the difference between the estimated ith level mean and the estimated grand mean, we can then estimate the level effect, where the estimated level effect alpha cap I is simply mu cap I minus mu cap. Now, what about the estimate of error variance sigma squared? We will come back to this after constructing a one-way ANOVA table. Please refer to example 6.1 again on 3 different types of alcohol used in a particular chemical process. Here we have equal sample sizes case where 3 observations representing the yields in percentages were randomly selected for 3 groups of different types of alcohol. The question addressed in this slide is to estimate the model parameters underlying a one-way ANOVA used in testing if there is any difference between the mean yields from different types of alcohol. Therefore, what you need to do first is to get the level total denoted by yi dot for all I equal to 1, 2, and 3 listed as follows. Summing up the level total, you can see here that the grand total denoted by y double dot can be found to be 778. Next, you may want to identify the sample sizes from each group like this. Again, notice that all sample sizes are equal, so we have equal sample sizes case in this example. Dividing the level total yi dot by the corresponding sample size ni, you will get the sample average for each level given by y bar I dot. This level or group sample averages are simply the estimated level mean denoted by mu hat I. In addition, dividing the grand total y double dot by the total sample size denoted by capital N, you will get y bar double dot given by 86.44, which is simply the estimated grand mean denoted by mu hat. So far, we have already estimated 4 model parameters, which include the 3 level means mu1, mu2, and mu3, and also the grand mean mu. Another 3 parameters to be estimated are the level effects, denoted by alpha I. Taking the difference between the ith estimated level mean and the estimated grand mean, you will obtain the following values, which are the ith estimated level effects denoted by alpha hat I. For example, to obtain the estimated level effect for the first level denoted by alpha hat 1, this can be done as follows, where we can calculate the difference between the estimated first level mean and the estimated grand mean, giving us a positive value of 0.89, indicating a positive effect. You can also see a positive effect for the second level, but a negative effect for the third level. Now, what if the sample sizes are unequal? Will you use the same method to estimate the model parameters? Let's look at another example in the next slide. Another example is on task 6.1 from the Statistics for Engineers textbook, page 133. In this example, we want to test if there is a difference between the amount of heat loss due to thermal paint type. Again, we have 3 different levels. That is, K is equal to 3. And the method to perform the statistical test is a one-way ANOVA. However, as you can see, the sample sizes are different, and the question addressed in this slide is to estimate the model parameters underlying the one-way ANOVA. As in the equal sample sizes case, we'll use the same method or calculation for this unequal sample sizes case. Therefore, you may first calculate the level total denoted by yi dot and the grand total y double dot, followed by identifying the ith level sample sizes N1, N2, and N3. Notice that in this unequal sample sizes case, the total sample size denoted by capital N is also the sum of all sample sizes given by 12. Dividing the level totals by the corresponding level sample sizes, you can obtain the estimated level means given as follows, whereas the grand mean is estimated by dividing the grand total by the total sample size capital N, which gives us the estimated grand mean of 14.92. Finally, by taking the difference between the estimated level means and the estimated grand mean, you will get the estimated level effect given as follows, where pain of type 1 has an indication of positive effect on the amount of heat loss, whereas pain of type 2 and 3 have negative effect on the amount of heat loss. Having done 2 examples on estimating the model parameters, we are at the end of part 1 on a one-way ANOVA chapter. Let's check again on the one-way ANOVA learning objectives. Hopefully by now, you should be able to write down the 2 statistical models, the assumptions and the constraint underlying a one-way ANOVA. You should also have an idea how to estimate the unknown model parameters. We'll look at how to achieve the other learning objectives in the next following part. Until then guys, Assalamualaikum warahmatullahi wabarakatuh and see you again in the next part very soon.